In this video, we are going to understand the need and working of our smart surge arrestor monitoring system. In traditional surge arrestor, when a surge occurs due to lightning or other transient events, the system only suppresses the surge but does not provide any information about the number of surges it has experienced or whether the last surge has partially damaged it. This lack of feedback makes it difficult to determine the health and reliability of the surge arrestor, potentially leading to an unexpected failure during critical conditions. To address this limitation, we propose a smart surge arrestor monitoring system. This system integrates MATLAB simulation with an STM32 microcontroller for real-time monitoring and analysis. By performing continuous FFT fast Fourier transform analysis on the input waveform, the system can detect changes in the arrestor's behavior, identify signs of degradation, and predict potential failure.
So, here we are going to understand the modeling of surge arrestor and transmission system of 12 kV. We are using the surge arrestor rated 8.4 kV, which is the MCOV maximum continuous operating voltage of 12 kV transmission line. We obtained the exact parameters for the surge arrestor to be modeled in Simulink via the VI characteristic curve and use it in the model where the surge arrestor is connected at the start of the transmission line. In this model, the voltage source is kept at 12 kV for the first condition, second condition lower voltage condition 13 kV and surge event 6000 kV. CP depicts the capacitance that is developed between the surge arrestor and the transmission lines. C3 and C4 when added give the equivalent capacitance developed between the parallel plates of the surge arrestor. R1 is the skin resistance of the housing of the surge arrestor. C1 is the capacitance developed between the skin current flowing and the metal oxide variestor used, where SiO2 and air are the dielectric. Line impedances indicated at the left top is the impedances of the transmission line. Here, the model at the right of C1 is the surge arrestor. Now we will take a look at the graphs, the leakage current graphs. During the normal operating condition, we get a sine wave having the peak value ranging between 3.75 and 3.9 milliamperes. Then we get a graph of overvoltage condition current flowing, which is a sine wave again, at the peak value at 4 milliamperes. Then at a surge event of 6000 kV occurs, the current waveform is peaked and has a value of 460 amperes.
By performing continuous FFT fast Fourier transform analysis on the input waveform, our system can detect early degradation patterns in surge arrestor as much as 2 to 3 months before an actual failure. To ensure high accuracy, we apply a Hanning window function to the input signal before performing the FFT. This minimizes the spectral leakage, resulting in a cleaner frequency domain representation. The FFT output is then analyzed to parse leakage current and surge events, calculate peak magnitude and RMS values of each FFT bin to precisely quantify surge severity. Evaluate total harmonic distortion, especially focus on third and fifth harmonics, which are the key indicators of insulation degradation and arrested health. The graph displays here represents real-time FFT data processed by our system. Each sharp spike in the graph corresponds to a surge event with the highest peak amplitude reaching nearly 1469 units, indicating a high energy lightning surge. The flat low-level regions between the spikes represents the normal background leakage current. Over time, a gradual increase in the baseline leakage signal suggests progressive deterioration of the surge arrestor's insulation. By tracking the peak magnitude and RMS value, we can monitor the energy of each surge and evaluate its impact on the arrestor.